So the task at hand is to say something about how Hamilton's principle and probably then Lagrange's equations actually change if you have a non-holonomic system instead of a holonomic system, which we've been working with so far. So for a non-holonomic system, all of these virtual variations, del qk, are no longer independent. And for concreteness, we will consider a specific case of non-holonomic constraints. Just see if I can get rid of that sound. So I'm naming this equation star because we'll use it in reference later. And the non-holonomic constraint is in a sum from k equals 1 to n over these terms here. You have a, l, k, which are coefficients, and then have an infinitesimal qk, and then possibly a coefficient related to time, a, l, t. And this, you have one equation for each L. Let's say you have up to m equations. Now, I remember in one of the first lectures, I think one of you asked me, is it possible to have a non-holonomic constraint which is written without an inequality sign? I think maybe that was you. This is one example. So it looks perhaps deceivingly a little bit like holonomic constraint. You have a function, something with qk here, something with t equals 0. But to see that this is not a holonomic constraint, just divide the entire equation on dt. Okay, so we get rid of this one. This is a constant, and then you have the derivatives of qk with respect to time. So this is a function of q dot, several q dots, which is equal to 0. Whereas the holonomic constraint required that you had a function of only q's, or the r's, only the coordinates, not their time derivatives. So this is also a possible non-holonomic constraint. And at first sight, it might look a bit artificial or tailored. Do we ever have a system where this is actually the constraints? Well, we're going to see that it's quite general actually in just a little while. So these coefficients may depend on the generalized coordinates and time. If we want to use Hamilton's principle or even derive Lagrange's equations from a differential principle, as we did initially, using these virtual displacements del q, we defined the virtual displacement as an infinitesimal change in q, which had to be in accordance with any constraints in the system, which makes it different from a usual differential, which is just a mathematical construction, so you can vary it in any direction. But the virtual displacement has to be in accordance with the constraints in the system. So if we want to make use of these del q's, this virtual displacement, they have to be in accordance with this constraint at a fixed time. If we want to make use of virtual displacements in order to use this variational principle to derive Lagrange's equations, they have to satisfy this constraint, which comes from this first term here. So they do so at a fixed time. So this term just drops out. Now, in order to proceed, we're going to make use of a method which is known as Lagrange's method of unknown coefficients. Has any one of you heard of that before? Yeah, I see some nodding faces. So it's a method you probably learned in some math course previously. And these unknown coefficients turn out to be very, very powerful, even though they're just something we introduced artificially. So what we do we multiply each of these virtual displacement equations that the virtual displacement have to satisfy with an unknown coefficient, lambda L, because we have L number of equations. We have M number of equations. L is just the index which characterizes which equation we're considering. And again, this unknown coefficient may be a function of the generalized coordinates in time. Well, if this is 0, this also has to be 0. I just sum over all else and integrate over time. I should have a dt here somewhere. Okay. Let me now combine this equation with the equation we have for Hamilton's principle for the virtual displacements. So keep in mind, we already have this, where we cannot just say that this is equal to 0 anymore, because we know that, oh sorry, it should be a virtual displacement there. Because we know that these are no longer independent due to the non-holonomic constraint. So let me combine this equation with this one. So I just added this term to this one. We still can't do very much. These virtual displacements del qk are still not independent. So we cannot say that the integrand has to be 0. So let me just try to visualize for you what the situation looks like now in terms of which variables that are independent and which are dependent on each other. So we have a total of small n generalized coordinates. We have small n generalized coordinates which come about by taking the original 3n degrees of freedom, if you consider three-dimensional space, and subtract any holonomic constraints. So n, small n, is equal to 3n minus all the holonomic constraints. Okay? And then we introduced m, number of non-holonomic constraints. That was the equation we wrote here, I think, in terms of these coefficients ALK and ALT. And we had m, number of those equations. So it means that n minus m of the generalized coordinates are independent on each other. But the rest here depend on each other through these non-holonomic constraints. Okay, so that's the situation at hand. We have this expression. We cannot say that this is 0 because all of these qk's are not independent. However, we do have one wildcard at our disposition which can help us. And that is these Lagrange multipliers, which we haven't specified, so we're free to choose them. So let's make a good choice. Let's choose these Lagrange multipliers so that this equation is satisfied for all k's from n minus m plus 1 up to n. In other words, in this regime. So we choose the Lagrange multipliers lambda so that this equation is satisfied for all of these dependent generalized coordinates. So if this is the case, then this is what we are left with. So notice that the difference here now is that the sum goes up to n minus m, because we discarded all of the terms from n minus m plus 1 up to n. So the difference between this expression and this one is how far the sum goes. N in this case, n minus m in this case. And now we're back in business, because we know that all of these virtual displacements are independent on each other. The n generalized coordinates minus the m non-holonomic constraints. So this means that we can now set this term equal to 0 for each k, because they're all independent on each other. So this is what we end up with. This equation has to be 0 for all k from 1 to n. Wait a minute, 1 to n? Didn't I just say that this equation is only valid for 1 up to n minus m? These are all independent, only up to n minus m. But now I'm claiming that this is actually valid for each k from 1 to n. How can I do that? The solution is all on this part of the blackboard. If you have a look at this equation, you see that it has exactly the same form, and we have chosen the Lagrange multipliers here so that it is valid for k from n minus n plus 1 up to n. So although these the vertical displacements qk are only independent up to n minus m, we have chosen lambda L so that this equation is also satisfied for the rest of the dependent coordinates. And therefore, it's valid from k equals 1 all the way up to n, which is what's written here. Okay, so let's try to get an overview of how many unknowns do we actually have. How many equations do we have? How many unknowns do we have? Is it possible to solve this system? We have n plus m number of unknowns. We have n unknown generalized coordinates, which are not all independent. And we have m number of Lagrange multipliers, or Lagrange constants. Do we have a sufficient number of equations to actually identify all of these unknowns? We do, and let me point out why. To begin with, we have n Lagrange equations. That's written over there. And they are modified from the non-holonomic constraints by the presence of the last term. In addition, we have m number of constraints, which I've now written like this to make it explicit that we have a dependence on q dot and not q, which makes it non-holonomic. So we have m plus m unknowns, m plus m equations. We should be able to solve the system. And after having introduced so many indices and new quantities, I think it's due time for an example. And the example is a ring rolling on an inclined plane. So the situation looks something like this. We have a ring with the radius r, and it's traveling down this inclined plane. And this movement may be characterized by two generalized coordinates. We have the position of the ring on the plane, given by this coordinate x. But if it's rolling, we should also characterize its angular position by this parameter theta. So you see then that we're actually mixing now Cartesian and polar coordinates. But this is perfectly okay. This is very natural in the Lagrange formalism, where we're only dealing with a generalized coordinate. So this can be anything. We can use x and theta or y and r, whatever. We do have now a constraint in the system. And the constraint is that the ring will roll. And this is to be contrasted with a situation where it only slips, where it just glides down the plane without rotating, for instance. So our constraint here is that it simply rolls down the inclined plane without ever slipping. So we need to write down this constraint equation in some way. Does anyone have a suggestion for how we can write down the constraint of a ring which is always rolling? Yes?
X equals r theta.
X equals r theta. Or in differential form we can write. And how do you reason to arrive at this expression?
Using what I know of mathematics and the distance on the outside of the ring.
So you're basically saying that the distance on the outside of the ring always has to match the distance traveled on the plane. This is what this expression says. Very good. Okay, so let's now make life a little bit easier for ourselves and assume that the ring is at rest to begin with. Zero start velocity. Okay, neglecting friction, we have a conservative system. The gravitational force can be written as a gradient of potential. Okay, so then we have to write down the Lagrangian. That's the first step. Find the Lagrangian. And for a conservative system, it's T minus V. Kinetic energy minus potential energy. Let's start with T. Well, assuming that large M is the mass of this ring, we should at least have something like this. Is that all? No? Uh-huh.
The angular energy, or the energy in the actual rolling mass.
Yes. If the ring was only sliding or gliding down this plane, that would be enough. But since we're now assuming that it's rotating or rolling, we also have to take into account the kinetic energy which is contained in the rotational motion. So that's just the angular velocity. It looks like this. The potential energy looks like this. So we have this factor sine phi, excuse me, where phi is the inclination of the plane, the angle of inclination of the plane, and L minus x is the distance. Yeah, so L I should define. L is just L is the total length of this plane. Our constraint equation looks like this. And if you look closely, this is in fact exactly the same form as the non-holonomic constraint we considered just 10 minutes ago. We now have just one constraint equation, so there's no need to attach any L index, because L was the number of constraints. It characterized the number of constraints, which would be M in total. So we have a sum from K1 to 2, because we have two generalized coordinates. And so if we write it in this form and compare this with our constraint equation, we may identify that AX has to be 1, A theta has to be minus R, and AT is simply 0. All right. Now we have to write down Lagrange's equations. And note that I'm adding now this term due to the fact that, that the generalized coordinates are no longer independent due to this constraint. So x and theta are not independent due to this constraint. So that has to be reflected through this term here, which we derived. So this is two equations. We have one equation for x, one equation for theta. So let's have a look at the x one first. If I obtain these terms here from the Lagrange function, t minus v, which I've written here, I get this. And keep in mind, ax is equal to 1. So we just get lambda here. That's x, and completely in the same way for theta. We get this, where I've now divided the entire equation on r, because a theta was equal to minus r. Okay, we have three equations and three unknowns. The unknowns are x, theta, and lambda. So we have two equations over there, and in addition we have the constraint equation. Which, if I derive this with respect to time, I get the double derivative of theta is equal to the double derivative of x, and r as a constant of proportionality. And that I should be able to put into the equation, the Lagrange equation for theta, to eliminate the double time derivative of theta. Which gives me this. Which, if I now take this and insert it into the Lagrange equation for x, gives me that. And also this. So putting this back into the constraint equation, I also have now an equation for theta. So So here's the result. We have managed to decouple all of the terms, x, theta, and lambda. The equation of motion for how x evolves with time is given here. The double derivative of x has to be a constant, given by g, 1/2 g sinus phi. Quite similarly for theta double dot, and then we also identified what lambda has to be. So just a couple of comments, because once you obtain a result in physics, you should check the mathematical structure of the result and see if it makes sense physically as well. So we see, for instance, that the acceleration here should be 1/2 of the component of the gravitational acceleration along the plane. We have neglected friction. Let's say that the ring didn't roll, that it just was sliding down the plane. What would you have expected for the acceleration of this process without any friction?
Twice that.
Twice. So if the ring wasn't rolling, you should have expected A is equal to g sine phi. But now it's 1/2 of g sine phi. It's smaller. The acceleration is smaller than if the ring was not rolling. Is this reasonable? Mm-hmm.
Yes.
Because?
Because half the energy goes to angular momentum.
Yes. You now have to consider that the kinetic energy consists not only of the movement along the plane, but also the rotational motion. So the acceleration along the plane is actually reduced, and it turns out 1/2 exactly. Right, so we used this method of Lagrange multipliers for a system where we had a constraint, so that the generalized coordinates were not independent. And we used a method which we derived from making an assumption about non-holonomic constraints. Would you say that the constraints in this case were non-holonomic? So for the example we just did, were the constraints non-holonomic? I see some skeptical faces at least. Well, consider the constraint. Or equivalently, does this look holonomic or non-holonomic to you? It's holonomic. It only depends on the generalized coordinates. So this actually shows that you can use this method of Lagrange multipliers on holonomic systems as well, where you have constraints. It's useful there as well in some cases. Perhaps it was a bit of an overkill in this case. We could have just substituted theta into x or vice versa to just end up with one generalized coordinate. But this was just to show you that this method works also if you have holonomic constraints. And one final point, well, let me write that. I'll take the final point next lecture. Thanks for today.